And our next speaker will be Valentina Zhelyazkova from ETH Zurich. And she will talk about ion molecule reactions near 0 Kelvin.
So, hello everybody. I'm very excited to be here and I want to thank the organizers for this wonderful opportunity. So, I'm very excited to tell you about some cold ion molecule reactions that we have been doing at ETH Zurich. But actually, maybe for the first talk today, I'm not going to talk about ion traps. And in fact, I'm actually not going to talk about ions at all because we don't have ions, but we have Rydberg atoms. And maybe that leads nicely from this question to my talk. And I'm going to focus on the effect of the lambda doubling on the rate coefficients of the helium plus NO reaction. So in our group, we're interested in barrierless, fast, and exothermic reactions involving the helium plus ion. So these reactions are actually really important for the synthesis of molecules in the interstellar media, as we heard already. So helium plus is abundant in space, and it takes part into a very complex reaction chain that leads to the synthesis of all hydrocarbons that we know. So these reactions are important in the otherwise very cold and tenuous interstellar medium. In other words, it's important to have precise knowledge of the rate constants, branching ratio, and energetics of these reactions, because then they can be used as input parameters for various astrophysical kinetic models. So experimentally, it's quite challenging to study reactions between ions and molecules at energies at below 10 Kelvin. So why is this so? Well, in your experiment, it's very easy to have a small potential difference. And even a potential difference of only 1 millivolt would lead to a heating of your ion to about 12 Kelvin. So in our group, we have a way to work around this problem, and it is to replace the helium ion by a helium atom in the Rydberg state. Basically, the idea is that the Rydberg electron moves on a large orbital radius, and then it's like tens of nanometers away from the core, and we assume that it only shoots the reaction between the positively charged core and the molecule, but does not influence it. So actually, this idea has been around for a while. It was first implemented in the group of Bill Chupka for the study of the H2 plus plus H2 reaction. And more recently, in our group in the Frederick Merck at ETH, again for the same reaction. And in fact, tomorrow we're going to hear a lot more about it from Johannes' talk. And there's also lots of theoretical and experimental work to demonstrate that indeed the Rydberg electron acts as a spectator. And this is the so-called independent particle model. So the fact that we have this Rydberg electron is actually very useful for us because it basically acts like a handle. What we do is we use a surface Rydberg Stark decelerator and deflector in order to merge our Rydberg heliums with a supersonic beam containing the molecule of interest. Okay, so I already have some schematic of our setup. So we have two supersonic beams, which are produced in these kind of homemade very short pulse valves, of which you can see kind of a render in this setup. So our helium valve is actually cryo-cooled, and at its opening, we have a discharge in which the metastable 1s2s triplet state is populated. Now, these metastable atoms travel, and then at some point, they get excited by a laser to a Rydberg state, and then they get captured in an electric field trap, which is formed above the surface of this 50 electrode Rydberg Stark deflector and decelerator. So once the two beams are merged, they enter in a time of wide mass spectrometer where we could detect the product ions of the reaction. So how do we vary the collision energy? Well, actually, we use this chip in order to set the velocity of the Rydberg atoms, while we keep the ground state beam a fixed velocity. So interestingly, so when we match the two velocities exactly, we have zero nominal collision energy with a small energy resolution of about 100 millikelvin. So that's really cold for us. So we heard already quite a lot about this Langevin model, but I'm just gonna remind you again what it is. So usually ion molecule reactions are described in terms of this Langevin model, which is really old. So it was first introduced in 1905, which tells you that the potential of the ion molecule reaction has only two terms. So there is a centrifugal energy term, which has to do with the angular momentum of the collision, and also an ion-induced dipole interaction. So in other words, you just assume that your molecule is a polarizable object, but it doesn't really have any structure, so there is no dipole or quadrupole moments to it. One can show that this sort of potential leads to a rate, the Langevin rate, which does not depend on the temperature or the collision energy, only on the reduced mass of the system and the polarizability of the molecule. What happens, however, at low collision energies is that you need to include the rotational state-dependent Stark shift of the molecule in the field of the ion. So why do these Stark shifts arise? Well, mostly they're because of the presence of a dipole or, to a lesser extent, quadrupole moments. So in this framework is the so-called adiabatic channel model, and it's been around since the late 80s. It was developed by Jürgen Troy and David Clary. So to give you a little bit of a flavor of our experiments, what we have done is we had looked at reactions between helium and highly powered symmetric top molecules with the example of ammonia and fluoromethane. And basically what we see, so here I just have lots of data, but so the point with the error bars is our experimental data, and we measure the yield of the reaction while we reduce the collision energy, say, from 40 to about 0 Kelvin. In all of these power molecules, we see that we have a significant enhancement of the yield as we go close to 0 Kelvin. And also, what you see is in these continuous covered points is our calculations based on the adiabatic channel model, which suggests that near zero, we get rates which are almost 30 times higher than the Langevin one. Basically, we see an increase with decreasing collision energy. So as a second type of reactions, we had also looked at molecules which have a negligible or no dipole moment, such as nitrogen, so this you see on the left, or carbon monoxide, which has a really small dipole moment. So in these systems, we actually saw the exact opposite effect. So as we decrease the collision energy, the reactivity is suppressed at 0 Kelvin. So what I want to focus today, however, is a different system, which is kind of a bridging point between the two cases. And it is the reaction between helium and nitric oxide. So why is this interesting? Well, so nitric oxide has a small dipole moment, but actually it has an electronic configuration with a single unpaired electron in a pi state. So why is that important? Well, so this molecule is well described in Helmholtz case A. And then the orbital angular momentum of the electron is non-zero. And it has, so the projection of this L on the internuclear axis, which we label by lambda, could be plus or minus 1. So basically what this means is that we have two states of opposite parity corresponding to the plus and minus 1. But because of interactions with higher lying electronic states, this degeneracy is lifted, so they're no longer degenerate. If you were to look at the rotational energy structure, we would see that each J level is composed of this, like, it's called the lambda doublet, with splitting, which increases as you increase the J, and also with alternating parity. So why is this interesting for us? Well, if we look at, say, the lowest J level in a small electric field, say going from 0 to 100 kilovolts per centimeter, we would see that these two parity states actually repel each other. And this means that the lowest component is basically has a strong negative and almost linear Stark shift at even low fields. If we now increase the field, and this is what you see on the left part of this panel, say if we go to 5,000 kilovolts per centimeter, but remember, so this electric field is generated by the ion, so right away we could convert it to distances to the ion r. So these sort of fields would be something like going from about 5.4 nanometers to 1.8 nanometers closer. So the lower, the blue state now is even more high field seeking, while the upper one is initially low field seeking, but then at some point it turns over and it also becomes a high field seeking state. Why does that change the reactivity? Well, in the middle panel, I just have the Langevin potential in black. And then what we see is that this blue state is much, much more attractive than the Langevin state. If we were to calculate the capture rate coefficient for this state, we would see that it dramatically increases as we decrease the collision energy, while the green state actually has a barrier, and it has reactivity that's completely suppressed until you get sufficient collision energy to overcome this potential energy barrier. So in our system, so we have a supersonic beam of nitric oxide, but there is a significant population in this J1 half state. And then in the J3 half, a similar effect also occurs. And basically, we're in a situation where these very highly enhanced states take over and dominate our behavior. So a little bit about the experimental data. So in this reaction, we could identify the M plus as the sole product ion. And then if we were to plot, so this is basically many data sets averaged together as a function of the collision energy. And what we notice is that as we go from about 9 to 1 Kelvin, there is almost no dependence. But then below 1 Kelvin, we see this really nice and sharp feature. And then we can also calculate it. And this is what you see in the blue dots. And we see that the calculation matches the experimental data really well, assuming we have a given rotational temperature in the beam. So this particular system is perhaps best to compare to the reaction between helium plus and carbon monoxide, because these two molecules are actually very similar in many ways. So they have almost the same mass, almost the same polarizability, very similar rotational constants, and almost the same dipole moments. So the only difference is that carbon monoxide has a sigma ground state, while nitric oxide has a pi ground state. And this is sufficient to kind of give you the complete opposite dependence on the reactivity. So in helium plus CO, we see this kind of decrease of the product Q or the K rate as you decrease the collision energy. And this effect is completely determined by the quadrupole moment. While we know this effect, it's the opposite, as I said, so we get an increase with decreasing collision energy. And this is dominated by the dipole moment. Okay, so I just wanted to thank the people working on my team. So I'm in the group of Frederick Mergt. So we have been very lucky to have two really good technicians. So this is Seppi Agner and Hans-Jörg Schmutz. And the data that I presented today was taken by one of our PhD students, Fernanda Martins, and also we had a semester project student, Serena Schilling. So thank you very much for your attention. Thank you.
So, thank you very much, Valentina. Questions on this talk? Who wants to start? Okay, let me start, maybe. So, do you see any possibility of selecting a specific lambda component in your experiment?
Yeah, so we're interested to do something like that. So actually what we have thought about is not maybe not kind of doing the opposite, going to a state that's less reactive. And we thought about using a coherent transfer of the population from this lower state to a higher, kind of slightly less reactive state. So with a millimeter wave, I think the frequency would work out just about right.
Johannes.
So initially you work with this Rydberg state, and you say that the Rydberg electron doesn't really play a role, but normally electrons play a big role, yeah, interacting with atoms and so on. So, so how can we explain this?
So I think there is there's probably true that there is interaction, say, between the molecule and the Rydberg electron. And then what we just assume is that not all collisions are reactive, but part of them are. And what we measure is not absolute rates, but relative rates. And then, yeah, we just don't know what is happening with the Rydberg electron. So basically, our reactivity would be a fraction of what the capture rate would tell you, let's say. That's a good question.
Have you thought about using other isotopes, like you did NH3 and ND3, but have you thought of doing the same study for the other molecules that you used?
Yeah, so we have. We usually like to have a good reason why we want to do it. So for the case of the nitric oxide, maybe it wouldn't make much sense because the dipole moment would be the same, and this is what gives us our dependence. But for some of the other systems that we looked at, and I didn't show it today, like we looked at an asymmetric top, ethylene, then it's actually quite interesting to look at an isotope of C2H2D2, for example, because there the nuclear spin statistics would be really different. So this is what we have next to do actually on our list of things to do.
Okay, I see no further questions. Then let's thank Valentina again.